Okay, the final talk of this session will be Ludovico Lami talking about irreversibility of entanglements. And just a comment, there will be an announcement following this talk, so please hang around just for a few minutes afterward.
Right. Can I have the slides? Yeah. Okay. Right. Welcome, everybody. Thanks a lot for coming. And, well, first of all, let me start by thanking the organizers for going through the extraordinary effort that was needed to put this conference together. So really, thanks a lot. It feels really good to be back at QIP. And I also want to thank my wonderful co-author, Bartosz Regula, who's also in the audience. He's been instrumental to this whole work. Okay, so the title is No Second Law of Entanglement Theory after all. So I guess we better start by understanding what a second law is in this setting, right? So what is entropy, first of all? The answer for this talk is just, it's a function that helps you understand what physical transformations are possible and which ones are not. For instance, so let's say that you have two compatible states of a system, that is two states that you are promised that they are connected by a physical transformation. So now the sense in which a transformation can happen is dictated by the entropy. So let's say that you have, I guess we don't see the full slide. Is there anything we can do to see the full slide? Yeah, better. Okay, so you have two states of a system and you are promised that they are compatible, like those. And now you ask yourself, fantastic, now this doesn't work anymore. Yeah, you ask yourself in what sense the transformation is possible. And the answer is that you compute the entropy, you understand that the entropy on the left is smaller than the entropy on the right. That means the transformation goes from left to right. Okay, so in fact, you can use the set of physical transformations, of physically allowed transformations to construct the entropy. So there is a whole axiomatic framework for thermodynamics that allows you to do this, right? So given the set of physically allowed transformations, you can construct a unique function under some axioms, a unique function that governs kind of the sense of physical transformations. Okay, and so that's going to be the entropy. When this is true, when this happens, that you have a single function that encodes all physical transformations, we say that there is a second law. And a consequence of this is that compatible states with the same entropy must be connected by reversible transformations, okay? So for instance, in standard thermodynamics, this is going to be the, say, Carnot cycles. Okay, so now we want to move this intuition from the resource theory, if you want, of thermodynamics, which is about work and heat, to the study of another quantum resource, that is entanglement, that we care about a lot, right? So the setting, I guess you all know, is you have a bipartite quantum system, bipartite Hilbert space, and so you have a special class of separable states there, the states that can be written in that form, and there is a very special entangled state that is the E-bit, the maximum entangled 2-qubit state. Okay, so the central questions of entanglement theory, which are very much intertwined, are, first of all, what kind of transformations can I perform on entangled states? And second, how do we quantify, say, mixed state entanglement, so entanglement of mixed states? Okay, so let's say that we start by looking at entanglement manipulation. Let's say that Alice and Bob can use some operations to manipulate their entanglement. And let's call the set of those operations F, okay? It's just a name for the set of allowed operations. For now, we are not going to say much more. So there are two fundamental tasks in entanglement manipulation. One is the entanglement distillation. You see, you start from a large number of IID copies of a given state rho, and you want to prepare as many E-bits as possible using transformations in F. Okay? So mathematically, it looks like this, and you're allowed to make an error epsilon in the transformation, but the important thing is that the error must go to 0. So and the number of copies of E-bits that you can get per copy of rho, that's called an achievable rate, and the largest possible achievable rates with operations in F is called the distillable entanglement under operations in F, or within the theory determined by F. Okay, so that's one task, entanglement distillation. There is also the opposite task, entanglement dilution, which works in the other way around, right? So you start from many copies, many E-bits, and you want to create as many copies as possible of rho, IID. Okay, and it looks exactly like it's kind of the converse definition, right? So, and now the the maximum number of copies of row per EBIT that you can create. That's called the entanglement cost of the state. Right. Okay, so it turns out that all reasonable entanglement measures within the theory determined by F lie between the distillable entanglement and entanglement cost. Particularly, the entanglement cost is always, it's never smaller than the distillable entanglement. And there can be a gap, and all entanglement measures must lie in that gap. Right, so the missing ingredient is, of course, what kind of operations F are we allowed to use? And the standard answer is, of course, LOCCs, local operations and classical communication. So that's a perfectly valid answer, and it kind of corresponds to a bottom-up approach, if you want. So you understand the basic building blocks, local operations and classical communication, and you say, whatever I can build out of those building blocks, that's going to be an allowed operation. So that's a perfectly valid approach. However, we argue that if you want to study a more general theory in which you have maybe some additional resources, you will go beyond this set of LOCCs. And a very good way to do this is to instead take a top-down approach, so an axiomatic approach, in which you don't look at the operations as something in a constructive way, but you just state some general principles that every physically allowed operation in whatever setting must satisfy. Okay? So I want to convince you that this first principle approach is actually helpful and important. So let's look at, again, thermodynamics. Okay, so the first time thermodynamics was invented was in the beginning of the 19th century, so actually 200 years ago, more or less. So the only thermal engine that they had out there was the steam engine, of course, right? But when Clausius and Kelvin stated the second laws, it was not stated in terms of steam engines, hot steam and coal and something like this. It was not in that form. Rather, it was stated as, what general physical processes can or cannot do, right? So, and the consequence of this is that the same principles apply to other thermal engines, right, like nuclear or solar power plants that were not out there at the time. Okay, so this is why first principles are important in general. So in the case of entanglement, what does this lead us to? Well, so it leads us to what people call usually a golden rule for the resource theory of entanglement in this case, which is that any operation that you use should not generate entanglement. So that means that whenever you plug in a separable state, the output should also be separable. So this is a general principle of consistency of the theory that we this is the kind of we want to be satisfied. Right. So now the main question is whether any theory, so that there's any set of operations F that complies with this golden rule, can satisfy a second law in the sense that we said before, right? Which is, of course, the same, as I explained, of reversibility, and is the same as having a unique entanglement measure. And of course, since you know the two extremal entanglement measures are the distillable entanglement and the entanglement cost, we want those to be equal for a special class F. Is that possible or not? So that's the main question. Turns out this is a reformulation of an old problem. And the old problem was posed by Martin Plenio in 2005. And he asked whether entanglement reversibility is possible at all. And if so, what is the smallest class of operations that can enable it? Okay, so we knew a few things prior to our work. So the first one is that local operations and classical communications, LOCCs, are not enough to achieve reversibility. So there's an old result by Vidal and Sirac and Vidal. Right, so, and we also know that even extending LOCCs to all PPT operations, that's also not enough. This was by Xin Wang et al. And on the other side, we knew that reversibility can be restored if you include operations that violate the golden rule just by a tiny bit. And yeah, so I guess the most fundamental open problem is still there, right? Whether you can actually have a set of operations that complies strictly with the golden rule, because like physical laws, we want them to be strictly observed, not just approximately observed. Like energy conservation, we want it to be something we want to be exact. Okay, so, and in fact, I mean, this is, so if you want, you can rephrase the question mathematically by asking yourself whether the entanglement is reversible under all non-entangling operations. Okay, so start from some intuition from other resource theories. So we said that before, classical and also quantum thermodynamics, they are both reversible under the maximal set of operations, or the set of operations that complies comply with the golden rule. Well, in fact, also under restricted set of operations. So turns out that also quantum thermodynamics of channels, that is also reversible. This was a result by Philippe Feist et al. Very recently. And so also the resource theory of quantum coherence, that's also reversible under its set of operations that complies with its golden rule. Okay, so I guess we should expect reversibility, right? And of course, the main result of this work is that this is not the case. So you can take all operations that comply with the golden rule, so all non-entangling operations, but still entanglement theory remains irreversible. Okay, and the way we show this is we exhibit a 2-qubit state, very simple one, and we can compute the distillable entanglement and entanglement cost, and there's a gap. So, yeah, so of course this means that there is no unique entanglement measure, right, to rule them all somewhat. So, yeah, so there is no equivalent in entanglement theory than the entropy in thermodynamics. And so that also means that entanglement is actually, it's really different and more complex than thermodynamics. And I want to stress once more that all other quantum or classical resource theories, they all are reversible under the same assumptions, right? So entanglement theory is really, it's really different. It's the first theory that is found to be irreversible in this setting. Okay, so proof ideas. So since we are QIP, I should pretend that the proof is very difficult, but in fact it is not. It is very simple, and it looks very much like a Western shootout. So there is a lot of staring at each other, but then the actual business is super short, but intense. So bonus points if you recognize the movie. If you don't, that's for a few dollars more. So you learn Italian also. Right. So, okay, so of course we have to establish a gap, right, between distillable entanglement and entanglement cost for omega-3. Okay, turns out the upper bound is easy. What is the upper bound on distillable entanglement is easy. The lower bound on entanglement cost, that's the hard part. I mean, hard in quotation marks. Right, so let's start by asking ourselves, when is it that an entanglement measure is, say, upper bounds the distillable entanglement or lower bounds the cost? Well, there is a standard answer if you look up in a standard textbook, and it is that the measure should satisfy these 3 conditions. First, normalization, weak additivity, and monotonicity under operations in F. These are kind of the standard axioms, but I want to draw your attention to the 4th axiom. There's a technical one, but it's actually crucial, and it is the asymptotic continuity. So it's basically a strong form of continuity for the measure E. That means continuity in trace norm. If you vary your state in trace norm, the measure shouldn't change much. And the crucial point there is this continuity constant CD that you find here, and that should depend logarithmically on the dimension, should be equal to the log of the local dimension. Okay, so these are the standard conditions, but then it turns out that there are some, these are not always necessary. And when I started thinking about this, I realized I didn't know this. So for example, there is a very notable measure of entanglement called the entanglement negativity. It's defined like this in terms of the partial transpose of the state. And that turns out to satisfy the first 3 axioms, but not the 4th one. It is not asymptotically continuous. And nevertheless, it turns out that it upper bounds the distillable entanglement under LOCCs. And so why is that? I realized I didn't know that. So I went all the way back to the proof of Vidal and Werner, who proved this. So they look at the arbitrary distillation protocol with LOCCs. And so then the proof looks like this. So you see there is the key step. So basically the key step is, one of the key steps is this weak continuity, in which you evaluate the measure for the target state, the E bits, in terms of the measure on the state that you actually get. And you see here there is it's a continuity, but here it's a weak continuity because here you have this very large constant that is linear in the dimension, that is exponential in the number of copies. So it's not logarithmic. So that's why this is not asymptotic continuity. But then you see, I want to draw your attention to a little miracle that happens, which is that you compute the value of the measure on the E bit, on the maximum entangled state, and it's this number, and this turns out to coincide with the continuity constant. So that's nothing short of a miracle, because then we can group the two together. And this is really unexpected. So, and then you take the log, divide by n, take the limit, and bam, here you get it. So again, the essence of the miracle is that the continuity constant of the measure coincides with the value of the measure itself. And that's really, really a miracle in a way. So we can adapt this intuition to our case. So you remember we want to do dilution, so the target state, let's say, is rho. So you can rewrite the entanglement negativity like this. You can rewrite it as a supremum, because there is a trace norm. You can write it as a supremum over some set of operators with bounded operator norm. Okay, so now you see immediately that the objective function, the continuity of the objective function is controlled by the operator norm of x. This is super simple to see. So, okay, so what about if we constrain the operator norm of x to be the same as the value of the objective function itself? Right? So that means, it looks like a circular reasoning, but it's not. It means defining this modified optimization, in which when it looks, it's the same as the one above, but I added one more condition. That is, the operator norm of x is equal to the value of the objective function. Okay, so here I rephrase the definition a little differently. You see I define this logarithmic tempered negativity, which is the log of this kind of modified negativity. It's called tempered negativity. You see here that I take the two states here to be the same, but in principle there are two different arguments. One is controls the objective function, and the other controls the operator norm of x. And the key thing here is that by construction, this satisfies what we call the epsilon lemma, which is exactly this type of continuity in which the continuity constant equals the value of the measure. Okay, so you see here that there's two numbers, they're the same. One is the continuity constant, the other is the value of the measure. And so that means you can group them together. Fantastic. So now you can run precisely the same proof as, well, kind of the same proof as in Vidal and Werner, and it works. And it works because not only because you have this kind of epsilon lemma, this continuity one, but then since this is also defined in terms of a maximization, you also get for free what is called a supermultiplicativity. So that means that you can evaluate the measure for n copies easily, can lower bound it by the value of the measure for one copy. So that's also for free from this method, and that's it. This is actually the proof of the simplest statement there. It's actually like this. You take the log, you divide by n, take the limit, and you get that the rate is always lower bounded by the logarithmic tempered negativity. Okay. Right. So notice that okay. So we have found a lower bound on the entanglement cost and the non-entangling operations. And turns out this is a semi-definite program, so this can be computed efficiently for finite dimensional states in, say, polynomial time. And I also argue that you should, even if you don't care at all about this axiomatic framework, you should still care about this measure, because of course it turns out to also be a lower bound on entanglement cost and the LOCC, so the standard entanglement cost. And this is not something you stumble upon every day, right? An SDP computable lower bound on entanglement cost. So yeah, I think you should care. Right, so now if you really want to conclude the proof, you construct this state omega-3, which is just, you take the projector onto the maximally correlated subspace, you subtract the maximally entangled state, and you get a rank 2 state, and that's your omega-3. So now, turns out you can compute the logarithmic tempered negativity, its value is 1. I don't know how to program, but I could do this by hand, so I promise it's easy. And so then now for the upper bound, as I said, just relative entropy upper bound works, and you get a lower bound, an upper bound which is 0.6 or something, so that's strictly less than 1. So here, yeah, it is irreversibility. So this is the end of the proof. Okay, so conclusions. Right, so for every class of operations that complies with the golden rule, we have proven irreversibility of entanglement theory on this state omega-3. That means that entanglement theory is kind of fundamentally reversible, so irreversible from first principles. And it also means that it is intrinsically different from thermodynamics and indeed from any resource that we knew of so far, both classical and quantum. And that means also that there is no unique entanglement measure to rule them all. Now, I would like to thank you, but before I do, there is a last slide, which is the price of reversibility. So what does it take to restore reversibility? So there is a result by Brandão and Plenio, as I said before, that you can achieve reversibility by employing channels that generate some entanglement. Okay, so they violate the golden rule by a tiny bit. So now the problem is, how much entanglement should you generate? And the answer depends on the measure. So if you quantify the entanglement according to certain measures, a small amount of entanglement is enough. But if you quantify it according to other measures, including the negativity that we have said, we have seen before, that the amount of entanglement that you must generate is exponential. So it takes a lot of violation of the golden rule to achieve reversibility. And with that, I really thank you.
Let me hop in real quick with a question. So in your proof, where does it break down if we look at this asymptotically non-entangling operations? What step would that be?
Yeah. So I mean, like the original definition, they use this the generalized robustness to prove to define these asymptotically non-entangling operations, and that is the problem there. Okay. So if you use the standard robustness of entanglement instead as the measure to quantify the entanglement, there is no problem. So you can still run this proof, but if you use the generalized robustness, then you see that this is not going to work.
Yeah. Okay.
Thanks for a nice talk.
Thanks, Mark.
So the concept of negativity appears in other resource theories, and so I think it's natural to think about tempered negativity in other resource theories. Have you done so, and if so, can you comment on that?
So we are starting to look into this, but yeah, so depending on the resource, there are measures that resemble the negativity, and we expect that some generalizations could be possible, yeah.
So if you talk about LLCC, that there are these, obviously, there's these two states, GHC, W, that can't be related under LLCC.
So can you come with it?
So
yeah.
These two states, GHC and W, W states that can't be related under LLCC operations, right? And so do you have some similar example in the case where you're looking at non-entangling, like the whole class of non-entangling operations, or is that sort of an opening question?
So there's two states, which states do you mean?
There's GHZ states and W states.
Right, okay,
yes.
So in
From one of
tripartite
the papers that you
entanglement.
cited, yeah. And this just sort of shows that, entanglement isn't reversible under LOCC, right? But then, you're showing that entanglement is also not reversible under any non-entangling operation. So do you have a similar kind of example, like a sort of, or is that still?
Yeah, I mean, if it's irreversible in the bipartite setting, it's going to be irreversible also in the tripartite. That's tripartite is more complicated. So you can always, clump two parties together, bunch them together, and that's going to help them. If they cannot achieve reversibility, even in the bipartite setting, that's
Okay, maybe my question wasn't clear, but I guess I'm just, these are nice touchstone examples, right? You have these two states that are not related under LOCC. Are there two states that aren't related under any non-entangling operation?
Okay, so so you mean the two states for which you cannot, so that kind of the rate is zero of transformation under non-entangling. So I don't think we know the answer to this, but we suspect the answer is that it's always possible to achieve, because we suspect that the distillable entanglement under non-entangling operations, it's always non-zero. So you can always distill some entanglement if you are willing to use all non-entangling operations from every state. That's kind of one of the claims of Brandau and Plenio. So that means that you can always generate some E-bits, and then from those you can generate any state that you want. So that's why the theory under non-entangling operations is actually stronger than the one under LOCCs. So because LOCCs, there is bound entanglement. So there are states for which that you can never distill. But under non-entangling operations, this is never the case. That's why, I mean, the theory is more powerful, but still it's not reversible. This is why it's non-trivial. It's not just it's not like just LOCCs done more generally. The theory is actually different. That was,
okay, thank you.
Welcome.
Yeah, we'll do one more.
One question via email from Jonathan Oppenheim.
Can you speak more louder?
Okay, one question from Jonathan Oppenheim. To make thermodynamics reversible, I need another large system, for example, a work system, and I allow vanishingly small probabilities that I lose work rather than gain work. In entanglement, shouldn't I also allow for an epsilon probability that I require a vanishingly small amount of entanglement to make the reverse transformation? It seems that your conclusion, for example, that you require a large amount of entanglement to make the reverse manipulation is about a particular measure which we know is not asymptotically continuous. Since what we care about are physical quantities, for example, the number of E-bits that are required or can be distilled, do your results apply to a physically meaningful quantity, allowing approximation?
So, so that I heard like everything perfectly, but so yeah, I mean the measure that you use is really crucial, and the thing is also the generalized robustness that is not asymptotically continuous. So that it's not very clear what measure to use to define the set of asymptotically non-entangling operations. And the point is, in information theory, is always, in my view, I mean that was I was taught, is always bad when you start by defining your task by putting in a measure that you came up with. Measures should always emerge from tasks, not, so that's why measures are given operation interpretations in this way. You should never start with a measure that you think is the right one and use that to define the task. So, I mean, like in information theory, entropy is always at the, at the theorem level. It's never at the hypothesis level, never to define the task. So I think it's always bad to put a measure that you came up with in the task.
Okay, thank you.
Okay, thank you.